Last month, our water bill showed that the usage doubled. So in this video, I'm going to show you how I got to the bottom of that using an ESP32 to monitor the water meter. And since we have the ESP32 there, I'm able to send the data up once a minute here to io.adafruit. And here it is plotted out. So we can monitor everything from showers, toilet flushes, doing the laundry, maybe you've got a leak somewhere. And I was able to actually figure out what was going on using this. And this gets even cooler because now, since I've got this feed up here, I can actually create devices which monitor water usage in real time. So check this out. This is a trig board monitoring water usage, which is activated as soon as the bathroom light is turned on. And it'll show you your usage in real time. I'll make a separate video on that coming up, but also what I might do is show, instead of gallons used, actually the cost of the water used for your shower. So when I first started this project, I went into it completely blind. Looking at the water meter here, you can see that there's some ECR terminals there, but I wanted this to be as non-invasive as possible, meaning I didn't want to tamper with anything going on the meter whatsoever. So I was thinking first let's sniff out those wireless signals that are coming out of the box outside where this cable goes, but looking into that a little bit, they're using some kind of frequency hopping algorithm, maybe some encryption. That would have turned into a much larger project and a lot more time than I wanted to spend on this. Also, I thought it would be cool to set up a little camera here and look at the display with a Raspberry Pi and process that. But again, a lot more time than I wanted to spend on it. So I looked around at the meter and I noticed that there is some kind of spinning wheel inside there. So I whipped up this little test board here, the Hall effect sensor that has a digital output hooked up to an LED. So I kind of swept that around while running the water. No luck there at all. So I kind of got discouraged and I'm searching around, seeing what else I could do. And I did find this Instructable where somebody actually was trying to do the same exact thing. And it turns out that the wheel inside the meter is magnetic, but it's so weak that these digital style Hall effect sensors, there's no way they could be tripped by that wheel. So you take an analog output style Hall effect sensor, like what they did here, which is extremely sensitive. And in this Instructable, they gained it up, and then you've got your output. So I figured, well, with the ESP32 and its 12-bit A to D, I might be able to read it directly and process it all in software. So the first thing I did, though, is just verify so that wheel could be read. So I did take a compass and kind of swept it around by running the water, and sure enough, you see the needle flip around back and forth. So I got to give big props here to this Instructable because I was ready to bail on this project altogether. And once I discovered that with the compass, I was good from there. So I went off, found this Hall effect sensor here, the DRV5056, and we're running it at 3.3 volts for the ESP32. Just down here at the cable side, there's the sensor. I've got it mounted to the lowest part there on the meter, and I had to kind of test it, riding it up and down to see where I was able to get the highest peaks out of it. And then right across the 3.3 and ground is a 0.1 microfarad capacitor, and then the output goes straight on over, cabled over to the ESP32. So on the hardware side of things, there's really not much to it. And I did kind of wish that I did add that buffer op amp and possibly even a comparator circuit, because in software it really was a challenge to get this all working right, and you'll see why. So we're going to talk about how the code works and everything, but I use this serial plotter tool within the Arduino IDE to fine-tune the system. And I've never really used this before, but it's extremely useful. So here you can see the data after I'm done processing it and zeroing it out. Right there, the red side there, that's where the threshold is for when it sees a pulse. So right now there's no water usage, but as you can see how sensitive that sensor is, it's got a lot of movement on it. So now I'm going to go flush a toilet upstairs and you will see what happens. And there you have it. So now you see we're getting a waveform, and it's very sinusoidal as that magnetic wheel is rotating within the meter. Now, a couple things to point out here is notice that the amplitude changes and the frequency of this waveform changes as the water flow changes. And there you go. So as the toilet there is finishing off, the amplitude is starting to decrease. Obviously, the frequency is decreasing. And just so you can see it, what I'm going to do now is go run the shower upstairs. So that's about 3 gallons per minute going. And you can see now we've got a very high frequency there. We're not missing any pulses. The amplitudes are kind of changing around a bit. But this is working great. And obviously I'm doing a lot of averaging on this, but which you'll see in the code. But this is kind of the gist of how it works. So basically what I'm doing is detecting the sine wave in here and converting it to a square wave. So these high pulses here in red are my pulses, and I'm converting pulses to gallons. So that's kind of how I figured this out. I ran it, I looked at the meter, I figured out what the difference was versus how many pulses I got. I converted the cubic feet to gallons, which there's some multiplier. I think it's 7.48 gallons per cubic foot of water used. Yeah, now that I've got that water meter going quick, you can see what the compass does. Okay, I just turned the water off, and did I mention you're probably going to get some exercise with this project? Going up and down the stairs, turning the water on and off, over and over and over again. Yeah. Alright, let's finally jump into this code. Now, we're using the IO.Adafruit library, so you're going to want to make sure you have that installed. Go to Sketch, Include Library, Manage Libraries, and then you can, in here, search for Adafruit space IO. And if you scroll down, you'll see it right here. So you want that installed. And if you go to the page for that and then click Dependencies, you will see, since we're loading this on an ESP32, obviously you need the latest version of the ESP32 core. And here's a tutorial here on how to install that, as well as the Adafruit MQTT library, which you can install using the library manager, and also the Arduino HTTP client library, which I've had problems with, so I'm not going to get into this too much, but let me show you how I fixed that. So when I was compiling the code, I was getting errors on this line and this line of this, and I think what I might do is have this available in the description below, so if you're having the same problem, you can just take this down. But all I had to do was put this here in parentheses as well as this down here, because you get this error like left side of this here, of this line is not, I forget what it is, but anyway, those are the two lines I had to change. I'm not even sure if the code uses this at all, but anyway, I fixed that by changing those two lines. So if you go to wherever your Arduino folder is, libraries, and then Arduino HTTP client, that file is right here in the source folder. Alright, so once you're all set up, we're going to load this on an ESP32. So in Tools, obviously you'll have the core already installed, so Node MCU 32S is what I'm using, and you should get a successful compile. This code actually started out from an IO.Adafruit example. So you see we've got the two tabs here. Config.h is where you would go and you set up your IO username and key. And so if you go over to where you log in there, and right here at the top right, this is io.adafruit.com. This is all free. You go to the AIO key here, you'll see your username and key. That's where you go copy and paste that out, put it in that config tab. And we are within the free limits here. So you see only 30 data points per minute is allowed in the free version. We're sending data once a minute, so no big deal there. And then if I go to my feeds, you'll see I've got one called gallons. So right here, gallons, and that's where we're actually sending this data to. And then it's pretty cool from there because we can create this dashboard. So there's my little weather station, and then all the way at the bottom, you see here is the last, what did I set this up for? You can change it. I have it showing the last 8 hours of usage. So if we do 24 hours, there we go. And you can see some showers in there. It's really cool stuff. Okay, so you change those two things, and then also you need a Wi-Fi connection. So there's where you put your SSID and password. Everything is hard-coded, and then you're good to go. So back over here now to the code, and you'll see right at the top here I have this line. So when I was showing you the plotter, which is right here in Tools, so that's right here, serial plotter, and that's what I was using before. So when this is actually like that, you would use the serial plotter just for testing the water meter data. But if we look at the serial monitor when we're in this normal running mode, when this is commented out, I'll just go ahead and reset it so you can see what it does. So the first thing it's doing right now is connecting to Adafruit IO. Well, actually, it's connecting to the Wi-Fi network, then to io.adafruit. And it grabs the latest value from the cloud because I'm not storing the pulse count in non-volatile memory. So if I had a power cycle or the Wi-Fi connection goes out, there would be no way for me to know what the latest value is. And when I go here, I don't want to like see this drop down to 0. I want this to always be incrementing up. And I could, here's something else that's cool. So if I go to my feeds, I could reset this. Like all I do is just add data, and if I set this to 0, it resets the system out because, or it would set it to 0 and I go and reboot the ESP32, and then I've essentially reset the system. So I could do that like once a month, once I get my water bill, if I want to compare the total usage for the entire month. So it gets the latest gallons, it converts that to pulses because that's all the ESP32 cares about is pulses. And then when it actually connects up to the cloud, it converts the pulses to gallons, and that's the only thing that's actually monitored in the cloud. All right, so going into the code here, then you'll see right here is where we set up the feed we're going to use for this. So we're calling it in the code gallons, and it in the cloud is labeled gallons. I always keep these things labeled the same exact way, so there's no confusion. So this is the feed name that I put in Adafruit, io.adafruit, and then in the code it's called gallons. And then right here in the setup, you'll see that only if we have water flow test mode not defined, we'll do this stuff here, because there's no need to do anything wireless when all we're doing is testing the magnetic wheel. So we go right in here connecting to Adafruit.io. It's actually also connecting to the Wi-Fi network. You see here io.connect. We set up the feed we're going to work with, and also the function callback here, handle message, which I'll talk about here in a second. So anytime data changes on gallons, this function is called so we can go and do something with that data. And then right here, what I want to do is check the connection status. This is actually the Wi-Fi connection. So if we're not ever connected, if this does not ever break out of this while loop, you see here we've got this 1 second delay. And if we ever increment connection try count here above 10, reboot the ESP32. So something went wrong for whatever reason. Maybe the Wi-Fi network's not up. Just reboot it and continuously reboot every 10 seconds until we break out of this while loop. After that, we know we're connected. Give us a little debug printout letting us know that we're connected. And then here's where we go and get the latest gallons from the cloud, which is very cool actually. I like this, that you can do this. So gallons get here. We'll go and get that. Then we go into this loop here, which all it's really doing is checking to see if that callback function was ever called. So we run this here, this io.run, and basically all we're doing is checking to see if first boot ever goes false. So I've got this global variable here called first boot, and that's equal to true. So in the handle function, it's all the way at the bottom here, when we do that get, this will be called as soon as the data comes in, and it comes in right here on data. So if first boot is true, then we know it's our first time booting up, and that's where we're waiting. So we set that to false, we receive that data here, we convert it to a float. Well, I print it out as a float there, and then I store it in gallons from cloud, convert it to a float, and then convert it to a pulse count. And I have a conversion factor here. So this code only cares about pulses. So every time, we see that magnetic wheel go around and we detect that high peak of the sine wave, we're incrementing a pulse count. So that's why we take the gallons from cloud and convert it to a pulse count with this conversion factor, which I figured out through testing. So that's what we do here, and that's what it's going to use from there on out in the code. So we're right here, and we're going through 500 here checks of io.run times 10. So it's 5 seconds worth here of checking to see if that data ever came through. And down there you saw that first boot is set to false. So as soon as this is not true, we break out of this, we know we're good. If here though, first boot, so if this went all the way through the 5 seconds, we're going to be right here. First boot was never set false. So right here, if this is true, that means it never was set false, and we reboot the ESP32 and try everything again. So we just got some fail safes in here because this thing is just sitting here in the basement. I don't want to ever have to worry about it. Wi-Fi goes out, power goes out, whatever. Just let the thing, fail safely, try to, fix itself. Okay, now we're in the loop, and here's where things get interesting. So again, we've got this not defined of water flow test mode. This is just for sending the data up every 60 seconds. So you see here we've got a little check there, and only if we're connected or not connected, here we'll reboot. So if something happened in the last 60 seconds, we check to see if we have a connection, and if we don't, just reboot, try to reconnect again. And this is how easy it is to use that io.adafruit library. See, gallons.save gallons used, and that pushes the data up to the cloud. That's all there is to it. All right, so if we scroll down a little bit here, you'll see that in the rolling averages code here, this is a bit of a science project, and this is where all of the tuning took place to get this to work, because if you think about it, you want the system to be sensitive enough that if I just turn the sink on upstairs, very little flow, I want to be able to detect that. But also, you saw how noisy it was even with no water flow, so I also have to average it out. And also, what if it's going up, like a sawtooth, or going up and down? I need to filter all of that noise out so I don't get double taps. And then also my sample rate down here. So we've got this delay of 10 milliseconds at the bottom of the loop. And also, I tweaked that. I tried running it faster, slower, and it seemed that 10 milliseconds was just about right for this. So basically what we're doing right here is keeping a rolling average. So as data comes in, data is also being deleted out of the array. So we have an entire array of 300 values. So the first thing we do is shift everything over, and that's what we're doing here. So we're going right up to value or position 298 in that array, and just basically, bringing everything in. So this would be at 0 to start, and this one's at 1, so it's just pulling over data that was in 1 over into 0, all the way on through. And also, while we're at it, get our average calculation ready. So we reset that to 0, and then start adding up all of the values in that array. And then I'm also keeping a short running average, which is only the last 30 values in that array. So this was just something I added in later on, and I'll explain why I did that in a second here. So now that the entire array is shifted over, you see here that the very last value, 299, is actually where we set the current value to. And then we finally add that last value to our total summation for the running average. Same thing for the short running average, and then we divide it out by the totals. So short is only 30, the whole running average is 300, and then down here is where we do our detection. So now that we have the averages, I was originally going to have thresholds on this. Yeah, so I just pulled this up here. So I want to show you that this is right around 0. So this is not straight from the Hall effect pin when I'm doing an analog read. That value is actually up at 600, and it's moving all over the place. It's going up past 700, it's coming back down. It's doing this whole crazy thing. And even when you're running the water, it's kind of got a sine, it's got a sine wave sort of look to it, but it's going up and down and up and down. So what I ended up doing was doing that running average on it, which isn't going to move like that. And then if I took the real-time value, subtract from that, then you get it around 0 like this. But even that was too noisy, so that's why I have the short running average on top of that, so that this value here, even around the running average, is still smoothed out somewhat. I hope that makes sense. So I call that the flat value. And the flat value is what I'm using to actually plot out. So if I didn't have any of this stuff here, which is only defined if or I should say only true if water flow test mode is not defined, I'm just printing out the flat value here, comma, the high pulse active. So I'm also plotting here the red square wave, and then we do a print line there at the end of it. So this needs to be your value, comma, separated with a final carriage return new line feed. Okay, so then based on the flat value, we actually do have a threshold. So the pulse threshold, like I mentioned before, was set to 3.2. And I've tested like 3.1, 3.5, and this was all part of the daily tests. Like, oh crap, I'm 2 gallons off. Am I high or low? Even when I have this noise here, when there's no water flow, you can see it's getting almost a little too close to that 3.2 threshold. In this case, it's not too bad. There's one. So, you don't want it to be like 2.9, where you're just barely touching it. But you also don't want this too high. Because, like I said, even with, the sync on just barely on, I want to be able to detect those pulses as well. So that's where we compare to. So only if we're above that pulse threshold, and also that the high pulse active is equal to false. So that's how we get the sort of the one shot. So if this is the case, it goes through, it sets this true so that this only happens once. Because when we're above the threshold, I don't want this every 10 milliseconds to be incrementing through. It won't become true again on the next high pulse from that sine wave. So right here we set that to true, and then if we're in the normal running mode here, you'll see we print out, we increment the pulse count. The gallons used is converted right here with our little multiplier here, which again was another thing that took me some time to figure out by testing, but I found that right here, conversion to 2 gallons constant is 0.03. So if I multiply my pulses by that, I can figure out what the gallon usage is. And that's all there really is to that. All this other stuff in here is just for debugging. Then right down here to reset that, to catch it on the next high pulse, you see here now if the flat value is less than, I have this -1 multiplier, so -3.2. So it has to go all the way negative to reset it. And this was previously set to true, which it would be there. Then we can set high pulse active to false. So now it reset it, and then on the next high side part of that sine wave, we will be able to reset this and set it to true. And that's it. So everything else there is for debugging and setting up the serial plotter. So I think in the next video, I'm going to show you that little monitor board I did with the trig board, which was really cool. So I hope you found this video interesting. Thanks for watching.